All right. Welcome, you wonderful educators, to EduSmart's Professional Development Series. I'm your favorite marketing coordinator, Devanshi Mathur. For those of you who are new to our series today, we bring the coolest education speakers to share with you their expertise. You get CPE certificates, you get to learn new things, and you get to hear our beautiful voices for 1 hour every other Wednesday. Today's webinar is filled with very engaging and very useful information. So without further ado, let me introduce to you our star for the evening. Lisa is known for offering challenging, creative, hands-on science educator workshops. She has over 34 years of experience in science education, with over 25 years in presenting at conference sessions and workshops for science teachers. She has worked as a classroom teacher, department chair, online certification teacher, virtual school curriculum designer, independent science consultant, and science curriculum director. Anything science and education related, Lisa has been there and done that. So without further ado, please give your warmest welcome to Lisa.
Thank you, Devanshi. Good afternoon, everyone. This presentation actually has a lot of video, just short video clips to show you. So I'm not going to use presentation mode so that I can make the videos larger as we get to them. So I'm just going to keep it here out of presentation mode. And when it's time to click to a video, you can see I have a lot of tabs open on the top here. So today our agenda is going to cover what exactly does a model, when kids are asked to model something, what does that mean? I'm going to show a few examples of modeling that we currently have in EduSmart resources, how to go from introducing a phenomenon to a final model. I have lots of different examples. How to scaffold model making and doing models with kids, because they can't just jump into full-blown modeling. If we have time, some brainstorming with Teagues for you to come up with ideas for how kids could model some of these topics. And then, of course, we will have time for question and answer. So what is a model? So models are things that are used to offer an external version of a mental concept. So I like to say it represents things that cannot be seen, such as forces or movement of particles. And scientists use models to help us understand and to explain how things work. So a model can be a three-dimensional copy or some kind of scale reproduction of an actual object or a process. And when we think about model, this is what a science teacher would normally think of, especially for elementary school. If you ask kids to model or to give a model or make a model, this is what you think of. But that's not the only way that kids model their thinking. So think about it as modeling is a way to make thinking visible. Because you'll hear me use that phrase quite a bit this afternoon. And so it can be a drawing, a physical object, it can be analogy, or sometimes when we're asking about weather or hurricane models, it can be a computer simulation. But the idea is it's a representation of knowledge that's formed through interaction with some kind of science phenomenon. And so you can see two examples here to the side. One is showing parts of a plant and it's labeled. So this is showing you that kids understand the model of the parts of a plant. So models can be very simple in elementary. This next one is about color perception. So I know you can't read the words that are on here, but you can see the kids draw pictures and write explanations to explain the pictures. And what this is doing is it's making their thinking visible. And so it's a simplified explanation. It doesn't need to explain every single detail, but it's just a way, again, to make thinking visible. So if we look into the new Teagues, I know we're not using them yet, but you're going to find that the term models show up a lot in our new Teagues. So all of these are either within the new science and engineering practices or with the new recurring themes and concepts. So these are just when it shows up for K-5. So you can see I highlighted models in red, that these are quite a few instances of the term model. And I believe in the current Teagues we have the word model in the process skills shows up once. So this is a lot different. It also shows up in the content Teagues. So again, these are just examples from elementary, Construct a model and explain the orbits of the sun, earth, moon in relation to one another. Making a physical model might be a better example of that, but you also could have kids do a scale model on paper to show more relative actual distances. Model and describe rapid changes in the Earth's surface. Okay, that one's they can model by showing. You can't really make a 3D model because it needs to move. But if you have a moving model, that would work, but they can just explain their thinking. And so you can see it shows up in 3rd through 5th here. We see the same thing in secondary TEKS for 6 through 8 and biology. It shows up a lot in the science and engineering practices, and then it shows up more in 6 through 8 with our recurring themes and concepts. We don't have those in high school. And then if we look at content TEKS for secondary, I just did through biology because that's all we have for high school in EduSmart. But you can see that the term model, whoop, one of them I didn't make red, so I'll fix that right now. That it shows up a lot. Using a model, showing modeling, using a model, that this term shows up a lot in our new TEKS. And let me do it this way. So we already have some examples of modeling in current resources. This is a 3rd grade unit on observing sound that we're going to connect to the new 3.8a. I don't remember the current number. What's causing sound to be visible, that they're going to have to explain that. Here's a 5th grade one that they are supposed to explain what causes the day and night cycle. What causes shadows, changes in shadow positions and shapes, that they can do that with modeling. And one here in 7th grade, how do properties of the ingredients of a solution change when it's formed? They can make their thinking visible and show this also by modeling. Here's the 8th grade one with talking about composting, a deeper dive into the discussion of conservation of mass and how matter cycles in an ecosystem is showing up all through the TEKS and the new ones. And so for that, we're just going to jump and do some examples. This first one, introduce the idea with a phenomenon, and you can ask the kids, can you draw a model of the states of matter? And just to show a example of this phenomenon, this is just Alka-Seltzer dropping in water. So we have a solid that we dropped in a liquid, and then what do we see being formed? Big gas. I'm not going to show the whole thing, but just to get you back to where we are. You have to start with a standard, so you have to make sure you know what you're covering. And so for this one, you could cover the 4th grade standard of physical states, also have physical states in 5th grade. We have physical states in 6th grade, physical changes in 7th grade, and we talk about kinetic energy of particles in 7th grade. So you could use this phenomenon in any of those grade levels. And so having them model states of matter or understanding a model of state of matter it is because they need to know more than just identify the state, like which one of these is a liquid. That's a pretty low level task for kids to do. And so they need to be able to understand this a lot better. And because to understand states of matter, you have to understand that particles are moving. This is a little hard to do with a 3-dimensional model. So a mental model is you want them to have an internal understanding of what's going on, and you want them to explain what's going on in terms of both matter and energy. So one of the ways I used to do this with students was to model states of matter with charades. And I think I have cards up here if I can get to them. Whoops, sorry about that. There they are. Let me do this. Where I'm giving you cards, Devanshi will send them out next week, where they can draw a card that looks like this. Your role is ice is increasing in temperature, but not melting. And they somehow have to do charades to show that, and have a small team have the rest of the class guess what that's going to be. And so this is a lot harder than it looks, and you really have to understand what's happening at the particulate nature of matter here to convey this. And so this is a way that you can do that. And I have rules for charades that I'll send you separately too, in addition to the slide deck that I use for this. So this is one way you could model the states of matter, is by actually acting it out and moving around. You probably have done something similar where you talk about how liquids move and then gases move, have more energy, but this is a lot more in-depth so that they can show you their thinking about something a little more complicated than just a simple example. So here's a phenomenon that has to do with sound. And so the idea is you want to have kids draw a model of what happens when loud music is played. So that is this video. Let me make it big. It's kind of obnoxious music, so I apologize for that.
I work with these guys.
That's probably enough to get the idea across. So what were some of the things you noticed? You can either unmute yourself or you can put something in the chat and Devanshi can tell me what you're saying. But did you notice something happened when the sound got loud?
So we have people in the chat typing in vibrations. I noticed vibrating windows, vibration on glass.
Good. Anybody see something in the car move?
Sound waves causing the solids to vibrate.
Okay. Okay, so
Started
these are good. We
jumping.
don't, oh, go ahead. Sorry.
Yep, that was the last one. It started
Okay.
jumping.
So you don't have to elicit every single thing that happened, but you want them to pay attention to cause and effect here. When we raise the level of the music, what are some of the effects that go on? And from your standpoint, you want to make sure you're starting with a standard that you can even start this as low as 3rd grade, that sound is energy that manifests itself by transferring energy from place to place and between objects. There's also a 4th grade a new TEK about transfer of energy with sound. And there's also one in 6th grade through transverse and longitudinal waves. So a little bit less aligned, but you could still cover it with this. And so you can take whole class observations, which is what I was asking you to do by typing in the chat. And so here are some things when done with the classroom of middle school students. The mirrors shook when the music was played. The windows were rattling when the bass notes lowered. The building windows were shaking. They appeared to be bending. The guy's shirt sleeve was shaking. If you look, the passenger's the coffee he had in his hand was moving. The rubbery things that hold the windows were shaking and bouncing. So you can see a lot of different things that they came up with. And so once they make observations, what you can do is ask them to make a visible or make an initial model. And so you can set up something where you ask them to explain what they think is happening. So this one had 3 parts: what's happening at the location where the sound is coming from, which was the car speaker, what's happening between the truck and the window of the building, what's happening at the window to make the windows move. And so you can see kids have their initial ideas. They're somehow showing sounds as particles. Okay, they're explaining the speaker starts off low, so there's little sound waves. The sound waves get bigger. The sound waves spread all the way to the window, and the force of the sound makes it move. So these are pretty good initial ideas. That's not exactly how things are working, but that's okay. You're getting their initial models. You're getting their thinking visible. Here's another example. I'm not going to go into the details or read this to you, but similar sort of thinking. And so you want to pull the whole class back together and somehow come up with some kind of consensus so that they all agree on certain topics or certain parts of this, because you're going to lead into more investigation for them to have a better idea of how this works. So for this particular class, they agreed there was a sound source and a sound receiver, and that something had to move in between the two. Something had to move between the car speaker and the window. So some more questions. Are these waves? Are they vibrations? Do they have energy? Everyone agreed we can hear sounds because they come from somewhere, and they're received because we can hear them. They know sound moves, but they're not sure if the sound should be represented as a particle or not. So these are all very good observations. And one thing I like to do before you have the kids start to investigate is set up a driving question board. And so all kinds of things came up on this driving question board. Questions about the waves, questions about sound receivers. Some people have some music background, so this has something to do with pitch. And then what about the volume? What about the speed? So you can see that they just have a lot of questions, which is also good. And then you ask them for how could we do a test or do some kind of investigation to find out more about how sound moves. And so this was a list come up with from the class. You're not going to have all the materials to do this. I actually have a pretty good lab that you could do at a lower grade level that I'm not going to talk about here, but if you're interested, you can let Devanshi know or let me know, and I'm happy to send it to you to get the idea that sound can make things move, that sound has energy, which is hard, I think, for elementary students to understand. So you're getting their ideas, and what you can do as a teacher is you can show them more examples. Let me close some of these windows now so I can get to the next video. Here's the one I want to show. So let's look closer at an instrument and play it in slow motion. So you want them to have this understanding that something's vibrating. Okay. Go back to our PowerPoint. And let's just make a model of how this drum is working. You could do this as a whole class even. So, or you could do the top part and have them fill in observations at the bottom. So the down stick hits the surface, it goes down, the surface rebounds, it gets less over time, the surface returns to the starting position, okay? And then to test more instruments, I have some more videos to look at. This one's really cool. It's a very old video, but it's someone who put an iPhone with the camera on inside a guitar. Sorry, I thought I had to queue it up to when it started. So you don't need to show the whole video, but it gets the idea across that something's vibrating. And this could even help kids understand in upper grades that sound moves as waves. Let me close some of these and get back to here. So now you want them, and hopefully they did a hands-on lab in class where they could understand some of these ideas. We didn't have time for you to come up with the lab and for us to conduct it today. I just showed you ways that you can give them more information. But when you ask for a final model of what's going on, without even reading the details of what someone wrote on this, you can see they understand the concept a lot better. That this sort of looks like how sound actually works, pretty good for a middle school student. Here's another one. She's got, or he's got a few more explanations, but we see this sort of pattern of close together, further apart, which looks like sound. And then this one, maybe this part is showing a pretty good representation of sound. And I like how the student made a close-up view So I put here, close-up views are always a good idea. So this is the one we're going to talk about in the most detail. We are going to sort of do one together. I had to pick something really simple to do, but does anyone have a question or comment before I move on to practicing this with you? So initial model, just to find out what they're thinking. You do research, you do experiments, and then you do another model. And the whole idea is to make their thinking visible.
We have a lot of people in the chat saying that the guitar video is very, very cool.
Yeah, I love that video. It's super old, but it still works to show the process. Okay, well, think about questions and we'll do them at the end. So this is a phenomenon where we're going to experiment with a demonstration. Because you don't have the materials in front of you to do this yourself, I'm just going to do a demo. And then, of course, with your students, you can set this up for them to do it on their own. We're going to talk about making a model of what happens inside of a straw when you drink something. And so again, start with the standard. I picked standards of the new TEKS, and you can see this one talks about forces, patterns of forces, equal and unequal forces. This one's forces, and here we have net force. So you can guess that I'm wanting to cover force with this one. So I think I'll stop here, stop sharing. So you can see me. Hey, Kelly, I didn't hear you. And let me stand back here. Can everyone see the cup of water I have? The straw. I probably should have worn white. Hold on. I got a blanket here. Maybe I can hold in front of me. Nope, it's too.
Looks like everyone can see ya.
Maybe this will help. My dinosaur blanket. Because there's color in the straw, and if I pick it up against a black dress, it's not going to show. So I'm not going to drink this because it's just colored water, but you may want to just show kids what happens when water goes up a straw. You may not need to show them. But we're going to talk about the forces involved here with just the straw sitting in the cup and when someone drinks through the straw. But you also want them to investigate forces when you do something a little out of the ordinary, which you've done and kids have probably already done, which is put your finger over the top of the straw and then pick it up. And let me get a piece of white paper instead of this. Maybe this will work better. I did not think this through about doing it online. And y'all can see there's blue liquid in the straw. Okay, so we're going to repeat with another straw. Because you always need to do these more than once. So let's try and see what happens with this straw. And can y'all tell what's happening?
The liquid's not remaining in the straw.
There's nothing in the straw, but this one, we can see something happening in the straw. So Devanchi's going to share a document with you that you can look at, and I'm going to go back to sharing my screen and pull it up here online. I think I have it pulled out a little bit at a time, but your document looks like this. Draw a model to show what happens when you drink through a straw. Draw arrows, label them to represent the forces involved. If you think there's liquid goes inside the straw when you take a sip, go ahead and color the liquid in. Then draw a model to show what happens when you're not drinking through the straw. Is there still liquid in here when you're not drinking? So you're trying to get their initial ideas about this. And then we're doing the experiment, which is what happens if you hold your finger over the top, have them draw arrows to represent the forces, fill in the liquid if you observe it in the straw. So this one we would fill in with liquid, right? At least halfway. This one didn't have any liquid. Okay, let me go back to my PowerPoint. So again, I put some more questions in here. When you drink through a straw, how does the liquid go up against gravity? Okay. You can get some whole class observations. You can just have them draw on that sheet. This is actually very easy to understand. I put some of the physics behind it here. This is just a joke. That was for you. But there's some complicated things going on just with drinking through a straw. You certainly don't have to explain it to this degree. So if it's just sitting there, is there liquid in the straw? If so, how did it get there? If you're not sucking through the straw to pull, they think you're pulling liquid up. I'll talk about that again in a minute. How does it get in if you're not sucking on the straw? So that's something to think about. And so what happens if you're not drinking? Draw arrows to represent the forces, fill in the liquid if you think it goes inside the straw. What are some other investigation ideas we could do? I already had one ready for you so that we could sort of model it. Again, start with a driving question board. I just used the same image and put the picture on top of it because I didn't have one set up for this one. And then time for investigation. So this is what I did. What happens if you hold your finger over the top of the straw and lift it? Why does the liquid not come out of the straw? And then what will happen on a second trial? Okay. So here are the pictures I showed you for trial 1. Here's trial 2. I just cut and pasted this from those sheets. Let's make a closer observation of the straw in trial 2. If you look closely, which you couldn't see, I poked a hole in the top of the one for trial 2. So what happened to the forces to make the liquid move? Here, the liquid didn't move, right? So forces were balanced. Here, the liquid did move, so the forces had to be unbalanced. So what's going on to do that? Okay, and then for your final model, I want you to explain why trial 2 had a different reaction than trial 1, and I want some balanced force diagrams here. Not with numbers, just with arrows showing what's going on, okay? So for a teacher guide, this isn't my drawing. I think in my notes, I have where I took the picture from, but you won't get that in the slide deck. Liquid goes up the straw because the pressure is less here. And why is the pressure lower? There's atmospheric pressure pushing down. And what happens is it pushes the liquid up the straw when the pressure's lower here. So why is the pressure lower here? Does anyone know? Not expected to know, but just in case. It has to do with Bernoulli's principle, that the faster a fluid is moving, the lower its pressure. And so that makes the pressure inside the straw less than the pressure of the atmosphere, and it pushes the liquid up. Kids do not have to be able to explain that part, okay? But you can add something back to their everyday life here. What would happen if the contents were something different that were very thick, like a milkshake? What happens the harder you suck on the straw with a milkshake? Does anyone know what happens to the straw?
It collapses.
It collapses. Okay. And that's because of the pressure. You're sucking so hard and trying to get that fluid to move that the atmospheric pressure actually pushes on both sides of the straw, not just pushing down on the top. So again, Bernoulli's principle. So also as a teacher guide, I'm talking about how these forces move. When you seal the top of the straw, it prevents air from going down inside the straw with a downward force on the liquid. So you only have the upward force of air pressure, okay? Kids don't understand that air pressure comes from all directions, and that upward force is stronger than the force of gravity pulling down on the liquid. Gravity still works right here, okay? But it's equal to the air pressure pushing up. So that's why it doesn't move. But if you take your finger off the top of the straw or you poke a hole in the straw, air can get in the straw, and now it can also push down. So you have air pushing down and gravity pushing down and only air pressure pushing up. And those are unequal forces. Everyone understand? Did I lose anybody here? So the force diagrams are actually pretty simple, okay? but you want them to change or have a better understanding from when you start just looking at that liquid in a straw till after you do an experiment and they do a final modeling, explaining their thinking. Okay. So this one was fairly simple. Sometimes these get complex, like we did with the one with the sound. And so here's one that I'm going to use as an example to show you how you can scaffold this. Because kids are not going to be able to go full blown. I know how to do a force diagram, or I know how to do to draw kinetic energy in different temperatures of water or something, because they will not be able to do that automatically. Hopefully, if you do this a lot, they'll get better and better at it. But let me go to this video. Let me close a couple more here. This is boiling water being thrown into cold air. Pretty short. I'll actually play it again because it's really fast. Okay, so back to my PowerPoint. So again, starting with the standard, here we're looking at changes in the state of matter. We're talking about thermal energy and transferring energy from place to place or between objects. We're comparing solids, liquids, and gases in terms of kinetic energy, relationship between temperature and kinetic energy. So what you want them to do as a model is explain what's happening when boiling water meets very cold air. So this would be, just give them the question and they have to draw pictures or explain, or you just give them a blank piece of paper and they fill it in. Most kids are not going to be able to do that. And so I wanted to show you examples of how you could scaffold this. And you'll get a print copy of this too, along with these slides, but you'll have it all in one place if you wanted to print it out. So same question, but here I put the picture from the video back in here. And I want to know what's happening to the water in the pan. And I also want to know what's happening to the water when it hits the air. Okay, so what's happened? The water in the pan is boiling. What is this up here? Is it water vapor? Yes or no from anybody? It is not water vapor. It turns to ice or to snow immediately. Okay. And if this is not scaffolded enough, here's another example of how you could do the scaffolded modeling. You have the same picture, the same question, but you give them more things to do. Here's a checklist. I have shown changes that water makes. I have shown the cause of the change. I have included labels for my diagram that you could draw in here. And I'm going to use all of these words when I do the explanation. So this is a great way to start, okay? And then hopefully they'll be able to move to this kind of modeling to eventually this kind of modeling. And the whole idea is to make their thinking visible. And all of these models can do that. It's just they have different degrees of scaffolding. So we're running a little low on time, so I'm not going to spend too much time on these other. I just wanted to give you more examples. So we've all seen this demonstration where the can of Coke sinks and the can of Diet Coke floats. And they'll come up and tell you that the can of Coke is more dense than, has a density greater than water. And the can of Coke has less density than the regular Coke. But what is inside the cans? Why is one of them more dense than the other? What does more dense look like? Okay, and so you can do all kinds of activities with floating and sinking and have them understand how to visually represent density, not just describe it or identify what's more dense, least dense, but actually understand what's going on. Here's another example. This is also a video, but I'm not going to show it. I want to know, what does the air inside the balloon look like at the beginning of this race? And what happens when you let go and the little car moves and the balloon gets smaller? So I want to know what the inside of the balloon looks like before and after, and what happened to the air inside the balloon. But this is a great example of how kids to do models. This is actually a cute video. I may just play it from here. It has annoying music as well. So this is, can you draw a model that explains why these drawings float on water? When you drew, it was probably on a transparency sheet, but you could use a sheet protector to do this. As long as you don't use a permanent marker, this will work, that these will float. You've probably seen something like this similar, but here you're asking them to draw a model to explain why these float on water. Here's another example. This is a before and after. That these are two liquids with a gate in between them. And when you pull the gate out, the red layer floats on top of the blue layer. Both liquids are water. So can you draw a model to explain why one of them floats on top of the other? So this is beyond a simple density. Okay, this is getting into temperature. So, you know, you probably already know that one of these is hot and one of them is cold. And so if they're both water, how can hot water be less dense than cold water? What does it look like? And so they don't have to know what a water molecule looks like. They can just represent it with dots. We're going to have to talk about particulate nature of matter in the new TEKS in elementary now. So this is a good one. Here's one that you could do in middle school, or maybe even better for chemistry. We have two kinds of soap, and one of them makes more bubbles than the other. So this would take some investigation and maybe some three-dimensional modeling before they finally understand how a soap bubble works. I have a whole lesson for this that I'm also more than happy to share. It was too long to do for today's. Then I had some practice where we could do some brainstorming, but I think we're going to be out of time because we want to have time for question and answer. But I'm just showing you words that can trigger when's a good time to do modeling. Here's explain in kindergarten, illustrate, explain, illustrate, explain, illustrate, illustrate, describe, describe. These are words that lend themselves to modeling. Relate, explain, describe, explain. Then I'm also giving you links to some more resources. There's a, you've heard of argument-driven inquiry. There's a trend now called model-based inquiry. This is really good. This has some templates for before and after models, like cause and effect, explanatory models, why teach models, how models support learning, supporting ongoing changes in thinking, that these are all really good links that might help you. And that is the end. We're getting to the question and answer part. If you don't already have it, make a note of my email address. I'm just lisa@edusmart.com, and I am more than happy to answer questions and share resources. You just have to ask. So I see there's a lot of stuff in the chat. So I don't know how much of it we're going to have time to cover, but I'm here as long as you want to ask questions.
Awesome. Lisa, do you mind continuing to share that last slide, please?
Yeah.
Thank you. So just going through, so as Lisa said, feel free at this point either to put your questions through the chat or unmute yourself to ask your questions. But to get us started, I'm just going to catch Lisa up on what you all have been putting in the chat so far.
Great.
So we have a lot of people who had great interest in the videos you'd sent. The boiling water video and the guitar video, huge hit. Everyone really enjoyed that. Also appreciated saying that the checklist is a fantastic addition to the model template. We have a few teachers who are interested in getting your lower grade labs and additional labs that you had shared. We have a teacher asking, can we please see the slide again with the resources list?
Oh, yeah. And you know, we're going to share the slide deck with you. but I'm not sure, are these links clickable in that slide deck, Devanshi?
I will check.
If
Let me
not,
check.
I will make sure we copy and paste this into something that is shared, you know, that you can just click on the link. And the same for the videos. I'll make sure you get a link to all the videos. They're in the notes, so I can grab those real easily as well. So you can go straight to the video.
Well, I'll also double check that on my side. Yep.
Yeah, we're not trying to keep you from getting to any of these resources. We're happy to share everything with you.
So before we start kind of wrapping up, and as a few teachers put in their last comments and questions, I wanted to take a moment to thank Lisa so much for taking the time for putting together this presentation. And thank you all teachers and educators today for joining us. I know you have a very busy time ahead of you, and the fact that you took time out to sit with us and learn about modeling is greatly appreciated. And Lisa, you're getting a bunch of thank yous in the chat.
Good.
Yeah,
I don't want you to be afraid of what model means and that you have to buy all these materials to build three-dimensional models of everything, that is not what modeling means. That just keep in mind that a model makes their thinking visible. So anything you can do where they explain their thinking is a model. Preferably with the drawing and to accompany the explanation, then you're good to go.
A few of the last comments we have. Thank you so much. I really enjoyed and appreciated this. You made my instructions so much easier.
Yeah.
And when are you hosting part 2 of the modeling series?
All right. All right, Kelly, you tell me what kind of information you want for part 2 and I can make it happen. I just wanted this to be something brief with lots and lots of examples, and I wanted it to be like not you know, threatening, like this is something that's going to be hard to do, because it is not.
And if you're anything like me, I'm the type of person who, as soon as I log out, is when I come up with all of my questions and ideas. So as Lisa said, you'll be receiving an email from me next week with all of the recordings, all of the resources that Lisa said she would share with you, as well as a copy of her slide deck. So please feel free to reply back to that, or as Lisa said, you can reach out to Lisa directly at lisa@edusmart.com, and we'll be glad to help you out. Our last comment of the day: I appreciate the simplicity of what you have shown. It will help me make the idea of adding models to the curriculum much less intimidating.
Yeah, exactly. That's exactly what I wanted from this. Modeling is not something hard to do. The kids are doing all the work. You need to set it in place and make sure it's scaffolded if they need it, but it's having them put what they think down on paper and show you that they understand, not just they can identify. It's a completely different way to look at it, but not difficult to do.
Wonderful. We have 2 more minutes for a Q&A, but just in case you all start wrapping up here, I'm going to sign off for EduSmart. Thank you, everybody, for joining us today.
Yeah, thanks for coming.
Hope you all have a great holiday season ahead of you. And thank you all for joining us this year.